Hey everyone, we're excited to present to you today our paper summarizing biomedical text with encoder decoder models. I'm Imran Qureshi with my partner Raul Padua, and to get right into it, we'll start with the problem.
Hi guys, talking about the problem, we tackled pretty much the generated report from medical images from doctors needing to summarize these complex findings efficiently and needing to make quick decisions on urgent patient cases. So also on the patient side, it's like a very sensitive taking out, like interpreting those impressions. So as background, we had radiologists needing to write reports to observe to write this observation on X-rays and synthesize those findings into impressions and hand off to other specialists. And here we introduce an architecture. It's a biomedical bird-to-bird model that will help radiologists generate concise impressions from reports, and we could reach a state-of-the-art performance and show you how right now. So as an approach, we had two pillars. So the first one was the model-centric approach, where we tested out several architectures and family of transformers, T5, bird-to-bird, and big bird. Some of them were already fine-tuned in specialized data sets in the medical space. To then shift into the data centricity approach, where we use the techniques to augment the data, shuffling the input fields that you can see in the screen in the bottom part, to significantly improve our impressions. So now I'm going to hand off to Imran to finish the presentation.
We also wanted to take a look at the robustness of our model across a variety of different disease types. So our data set, the MIMIC6R data set, is comprised of multiple different diseases like cardiomegaly. And interestingly, our bird-to-bird model performs very well across these disease types, not many class imbalances. But there is a big imbalance between no findings and the other diseases. We hypothesize that this is because no findings is a smaller space of possible impressions. You can achieve a very good root score just by simply outputting no findings found in this class. So we found that the model learned to output that when it detects no findings. So it performs very well, almost double the performance of other diseases, which is a place for future improvement and kind of for improving these class imbalances. We also want to take a look at why these other models, that are bigger, having linear attention or fine-tuned on previous and biomedical data sets, didn't perform as well as this vanilla bird-to-bird model. We noticed that our context is actually focused on one or two sections, which is the findings, indication, and comparison of our report. So because we knew that ahead of time, the linear attention mechanisms of Big Bird were not as useful because those sections are 100, 200 tokens. So the Big Bird model just didn't have much of an advantage because the context wasn't spread out across the document. Finally, our fine-tuned checkpoints on PubMed or clinical didn't perform as well because we noticed that this task of summarization was quite different than the statistical distribution that those fine-tuned checkpoints were trained on. We also want to look at what knowledge the model has learned. So interestingly, the model is not just learning random statistical patterns in our data set. It's learning important anatomical and physiological facts of our data, such as no and negation is associated with normal anatomical features, or the fact that pneumonia is associated with pleural surfaces of the lung, and then like chest is associated with heart, lung, and the mediastinum region. So these are very important kind of knowledge that is being learned that could eventually be extracted in future work. Here's a table of all the different models we've trained and the different results we've got in the experiments we ran. So we noticed that the fine-tuned bird-to-bird model performed best, even though it needed less training time and less model space versus the other models like fine-tuned Big Bird or T5 long. And to conclude, we present a new bird-to-bird model, which presents state-of-the-art performance in our radiology summarization task, using both the architecture search as well as the data-centric data augmentation approach by shuffling data. We also look at the analysis of the disease and how we gain knowledge in the model, and future work could include improving on these class imbalances. So we were really excited to do this project, and we're really excited to see where this will go in terms of future work. Thanks for listening.
Thanks.